atomic structure, first year chapter. This is for the coming board exams. LAQs they'll ask from atomic structure. In atomic structure, we have two very important long answer questions. So let us see the two long answer questions. From these two, one question is compulsory in the board exam. The first one is write the postulates of Bohr's model of hydrogen atom. Discuss importance of this model to explain various series of line spectra in hydrogen atom. So this is related to Bohr's atomic model. Let us see the postulates of Bohr's atomic model. The first postulate of this theory is the electron in a hydrogen atom revolves around the nucleus in a fixed circular paths. These circular paths are called as orbits. So here I'm writing underlining important points. You have to focus on that underlined words. Next, each orbit is associated with a definite energy. So these are called as energy levels or energy shells. These energy cells are represented as 1, 2, 3, 4 or KLMN from the side of the nucleus. So here below this point there is a diagram. So each orbit is represented with the alphabets, that is K, L, M, like this, or you can also represent with the N. N is equals to 1, 2, 3, 4 and so on. Next, as long as electron revolves in an orbit, it neither loses nor gains energy. So the energy of the electron in an orbit remains constant. Hence, these orbits are called stationary orbits. Next, coming to the fifth point, the angular momentum of electron is always integral multiple of h by 2 phi. So this we can write mathematically as mvr is equals to nh by 2 phi. So here in this formula, what is m, what is v, what is r and nh is given below. M is nothing but mass of electron, v is velocity of electron, whereas r is radius of an orbit, and h is Planck constant, and n is principal quantum number. Even you can also write Planck constant value also, which is 6.625 into 10 to the power minus 27 erg second, or you can also write it as 6.625 into 10 to the power minus 34 joule second. So these are the values in ergs and joules. And coming to the sixth point, if an electron jumps from one level to another level, it may emit or absorbs energy. So that energy difference we can calculate with the help of formula, that is delta E is equals to E2 minus E1, which is equals to h nu. You can write because E is equals to h nu. We have a formula. Next, coming to the seventh point, if electron jumps from lower orbit to higher orbit, it absorbs energy. If electron jumps from higher orbit to lower orbit, then it emits energy. So these are the important postulates in Bohr's atomic model. Now let us see Bohr's explanation to hydrogen spectrum. So this is very important, that is hydrogen spectrum. Let us see what lines are present, how this hydrogen spectrum is formed. Hydrogen atom has one proton and one electron in the ground state. There is no neutron. Next, second point is, by the absorption of 13.56 electron volts energy, electron jumps to higher energy level, which is unstable. So whenever electron jumps to higher energy level, its position is unstable in higher energy level. That is the reason it is trying to come back to its original place. Hence, it comes back to ground state by emitting the energy. Means when it is coming back to the ground state, it is emitting the energy. Coming to the third point, the emission of energy may occur in one step or in several steps. Since a sample of hydrogen contains many atoms, several spectral lines are formed. So they are Lyman series, Balmer series, Paschen series, bracket series, Fund series, and also Humphrey, you can write Humphrey series. And here they have given name of the series and its n1 n2 values and spectral region also given. Lyman series is the first series in the hydrogen spectrum, then Balmer series, Paschen, bracket, and P fund, and the last one you can add Humphrey series. And n1 value is considered as 6, n2 starts from 7, 8, 9, 10, so on. And here this is also observed in for IR region. So here spectrum is given. Let us see. This is the ground state. When electron is coming from any higher energy level, that may be second to first or third to first or fourth to first, a group of lines are formed. For that group of lines, the name is given as Lyman series. The same way, when electron is coming from any higher energy level to the second energy level, for that a series of lines, the name is given as Balmer series. The same way, any higher energy level to third energy level, that is Paschen series, fourth energy level bracket, fifth energy level is P fund series, and sixth energy level is Humphrey series. Which is also observed in far IR region. So this is the hydrogen spectrum, and this diagram is very important in LAQ. If you miss any point, you may lose marks. Now, according to that hydrogen spectrum, we can calculate wavelength, wave number also. The wave number and wavelength of these spectral lines can be calculated by using Rydberg's equation. So here Rydberg's equation is given, that is nu bar is equals to 1 by lambda, which is equals to RH into Z square. Also you can write 1 by n1 square minus 1 by n2 square, where R is nothing but Rydberg's constant. RH also you can write, whose value is 109677 centimeter inverse. So here n1 is nothing but lower orbit, n2 is higher orbit. So this is about the first LAQ in atomic structure. Next, coming to the second LAQ, that is quantum numbers. So this is also very important, and from these two any one question they'll ask. So let us start in the second LAQ, that is quantum numbers. How are the quantum numbers N, L, M and S arrived, and explain the significance of these quantum numbers. So let us start. The quantum numbers N, L and M are arrived from Schrödinger wave equation, and quantum numbers are introduced to explain main shell, subshell, orientation and spin of the electrons. So we have four quantum numbers. Let us see that four quantum numbers. The first one is principal quantum number, the second one is azimuthal quantum number, and the third one is magnetic quantum number, the fourth one is spin quantum number. Let us see one by one what is principal quantum number and what are the main points in this principal quantum number. Let us discuss. This principal quantum number was proposed by Niels Bohr and it is denoted by N. These 2 points are very important, so I am underlining under that 2 points. Next, second point is total number of subshells for a given value of N is equals to N. Whereas the third point is the total number of orbitals for a given value of N is equals to N square. And the maximum number of electrons for a given value of N is equals to 2n square. We all know that where n represent orbit number. So in orbit, how many orbitals are present, how many electrons are present, that we can calculate with the help of principal quantum number. And a significance of this principal quantum number, if you see, it indicates size of an orbit and energy of the electron. Second one, azimuthal quantum number, which is also called as orbital angular momentum or subsidiary quantum number. So this quantum number was proposed by Sommerfeld and it is denoted by L. Values of L depends on n. That means azimuthal quantum number depends on principal quantum number. The values of L are from 0 to n minus 1. That means you can write 0, 1, 2, 3, so on, n minus 1 you can write. So these are the azimuthal quantum number values. When L values are, see here they have given 0, 1, 2, 3, the subshells are called S, P, D, F respectively. That means, for example, L is equals to 0, that represent S orbital, L is equals to 1, which represents P orbital, L is equals to 2 represents D orbital, L is equals to 3 represents F orbital. Next, so the number of subshells for a given value of n is equals to n value, that is equals to n only you can say. And the significance of this azimuthal quantum number is it indicates shape of the orbital. Azimuthal quantum number indicates shapes of the orbitals. Next, coming to the third quantum number, that is magnetic quantum number, which is proposed by Landé and it is denoted by small m. The values of m depends on L. The values of m are from minus L to plus L including 0. Next, the total m values are orbitals in subshell is equals to 2L plus 1. So this is the formula. By using this formula, total m values of orbital can be calculated. And the number of orbitals in S, P, D and F subshells are 1, 3, 5, 7. For example, if you consider S orbital, only one orbital is present, there is no suborbitals. If you take P orbitals, it contains 3 suborbitals and D5, F is 7. The number of electrons in a subshell is equals to 2 into 2L plus 1 is the formula. Total number of electrons in S, P, D and F are 2, 6, 10 and 14. That means S orbital accommodates 2 electrons, P orbital accommodates 6 electrons, D orbital accommodates 10 electrons, F orbital accommodates 14 electrons. Next, the last one is spin quantum number. The spin quantum number was proposed by Goudsmit and Uhlenbeck and it is denoted by S. So it is independent. That means the spin quantum number is not depending on any other quantum numbers. That means principal, azimuthal, magnetic quantum numbers, if you consider, they are depending one on another. But whereas spin quantum number is independent. And the values of this S are plus of and minus of. This plus of and minus of represents spin of the electron. If the electron revolves in clockwise direction, which is represented with the upward direction, that is upward arrow, spin is given as plus of. Clockwise direction is plus of, whereas electron revolves in anti-clockwise, which is represented with downward arrow, and the spin is given as minus half. Maximum number of electrons in an orbital is equals to 2. Any orbital can accommodate 2 electrons. The maximum number of electrons present in S, P, D and F subshells are 2, 6, 10, 14 respectively. And coming to the significance, it indicates the direction of the spin of the electron. So these are the important points and significances of different types of quantum numbers.